Road to Olympiad.
Welcome to RTO. Consider the following problems. Find all positive primes p for which there exists positive integer n, x and y such that p to the power of n is equal to x cubed plus y cubed. Fermat Last Theorem tells us that there does not exist solutions for the case when n is equal to 3. However, what if n is not equal to 3? How many solutions do we have if we restrict the p to be prime? Pause the video if you like to give this problem a try, and when you are ready, keep watching to learn how to solve it. To solve these problems, we start by finding some easy example for which it works. We can easily see that there are solutions for p is equal to 2 and p is equal to 3. In particular, for p is equal to 2, we have 2 to the power of 1 is equal to 1 cubed plus 1 cubed. And for p is equal to 3, we can have 3 square is equal to 1 cubed plus 2 cubed. We claim that there is no solution for p greater than 3. To do so, we assume to the contrary that there is solution for p greater than 3, and we choose the positive integer n, x and y such that the n is the smallest. Notice that we can factorize x cubed plus y cubed as x plus y times x squared minus xy plus y squared. Here, x and y cannot be both 1. Else, we will get 1 cubed plus 1 cubed is equal to 2, which gives us p is equal to 2 and n is equal to 1. This is not what we want. In this sense, both x plus y and x squared minus xy plus y squared must be greater than 1. X plus y is greater than 1 is obvious because both x and y are positive. As for x squared minus xy plus y squared, we can rewrite it as x minus y the whole thing square plus xy. Even x minus y could be 0, but from the condition x and y cannot be both 1, we must have xy must be greater than 1 as well. Thus, this gives us x squared minus xy plus y squared is greater than 1. Now, since both x plus y and x squared minus xy plus y squared is greater than 1, and their product is a power of a prime number p, it follows that both x plus y and x squared minus xy plus y squared is a multiple of p. In fact, they are both a power of p. Therefore, x plus y the whole thing square minus x squared minus xy plus y squared, which is equal to 3y, must be also a multiple of p. Since p is greater than 3, p must divide at least one of x and y. However, since x plus y is a multiple of p as well, it must be the case that p divide both x and y. However, in these situations, we can divide the given equations by p cubed and obtain this one. Notice that both x over p and y over p are still positive integers because both x and y are divisible by p. And n minus 3 is a positive integer because n is greater than 3 from the fact that both x and y are multiple of p, so x plus y must be at least 2p, and x squared minus xy plus y squared must be at least p squared as well. So their product must be greater than 3p cubed, which the minimum it can be is p to the power of 4. Thus, this leads us to a contradiction. As from the assumption above, we have fixed that n is the smallest integer for p greater than 3 to have a solution. Therefore, p is equal to 2 and p is equal to 3 are the only primes that works for the equations, And this marked the end of our solutions. Post in the comment below if you have any thoughts on the video, and if you haven't subscribed yet, consider subscribing. This will really help us out. Anyway, see you in the next video. Thank you.